Okay, in this practical, you'll be working with capacitors. You'll be charging them and then discharging them. And as this happens, you'll be measuring the voltage and how that changes with time. In my class, you'll be tested on the following CPACs. 1A, that you can follow written instructions that will be given to you and that you can set up the circuit correctly. And then 4A and 4B, that you can take the accurate measurements, the correct things, and that you can record this correctly into a table. During the practical, given some equipment that look like this. Okay, some cells from normally 1.5 volt cells, and then you got a capacitor, maybe a range of capacitors, a two-way switch which you can switch to the left and to the right, so you can control the direction of the current flow. Some wires, a few resistors with different resistance, a voltmeter, a timer, and a normal switch that is just on and off. Remember, during the practical, you need to make sure you connect the capacitor the right way around. Okay, so this end here is a negative end, and it's got this negative symbol on the side of the capacitor, and also the metal bit that's sticking out of it is shorter on the negative end. Okay, so ensure you connect this the right way around, so it should look like this. The negative bit should connect to the negative terminal of the cell, and the positive to the positive. And the voltage you should be using is, you should be less than 35, okay? But the truth is you'll be using significantly less, so there's no real risk of the capacitor exploding or anything like that. During the practical, you'll be tested on how well you can follow written instructions. So let's start with the discharging one. So you'll be given some instruction like this. Okay, I want you to pause the video and read this. Okay, so some important bits is making sure that you connect the polarity correctly, and then you set up the circuit like is shown in the diagram here, and then you actually start doing a trial discharge first before you start taking measurements to check everything is working correctly. Here's the second bit of the instruction. Pause the video and read it. Some bits that I want to point out is that you should use your phones to video the voltmeter and the stop clock, and then once you've videoed it, you should re-watch the video and record the voltage every 5 seconds on the stop clock. Now if it's discharging very slowly, then you can record it every 10 seconds. Okay, then use the experiment all over again but with a different resistor. So repeat it with a different resistor and record the voltage out. Now to analyze the data and plot the graphs, I want you to do that after you've done the charging circuit. Okay, so here's the instruction for the charging part. Okay, so you're going to set it up like this, so you can see you have to disconnect your circuit and set it up again. And bits that I want to point out is that you should again do a trial charge to check that it's charging correctly. Once you've charged it up, you can discharge it very quickly by just connecting a low resistance resistor across the ends of the capacitor. So if your capacitor looks like this, just connect the low resistance resistor, like maybe a 10 ohm resistor, across the ends, and that will discharge the capacitor very quickly, so you can redo the experiment again. Here's the second bit of the instructions, so pause it and read it. Okay, so firstly you close the switch and you start the stop clock, and you can use your phones to record a video of the voltmeter and the stop clock. And once the practical is done, you're going to take the data from your video. Every 5 seconds you're going to write down the voltage into your table, 10 seconds if it's a very slow charging process. And then once again you're going to repeat this with another capacitor or resistor, so the different combination. So all in total you'd have 4 sets of data, each one with a different combination of capacitor and resistors, and also some charging and some discharging. So before you start the practical, make sure you have some tables to record your results. So along with the time and the voltage, you'd also need to record down the capacitance of the capacitor that you use and the resistance of the resistor that you use. Make sure that you write all of these down with the correct unit. So in the columns, you don't have to write down the units again and again, just write down seconds at the top and the voltage like so. But with the capacitance, make sure you use microfarads, that's the best unit there. And the resistance may either kilo ohms or ohms, that's fine. Okay, so in any given column when you're recording data, you need to make sure it's to the same decimal place and that you're writing down what you see on the screen accurately. And finally, you might want to add another column, especially for the discharging circuit, because you can have a log graph as well. So you write down log of voltage, but now the voltage units, volts, must be inside the brackets like shown here. Once you've recorded 4 sets of data, 2 for charging, 2 for discharging, you're ready to plot the graphs. So let's start with potential difference against time for a discharging circuit. It will look a bit like this. Okay, it's an exponential decrease. And then if you use a resistor with a higher resistance, you might have used a lower resistance, but if you use a higher resistance one, then it would discharge more slowly, so it would look a bit like this. So you can plot this on one graph. Okay, and then for the charging circuit, the voltage will increase like so and level off at V0, which is the maximum voltage you can have. And if you used a resistor with a higher resistance, it will take longer to charge up. So it will look like this. However, these graphs are not that useful. So what's more useful, especially for the discharging circuit, is if you take natural logs on both sides and plot that. So let me show you what that looks like. So you take the equation for the discharging voltage, okay, and then take natural logs on both sides. Then using the log rules that you would have learned in maths, you can split this up like so. And then actually ln to the e to the power of minus t over rc becomes just t over rc like so. Okay, and then you can compare that to the equation of line y equals mx plus c. And let me write down in this form so it's a bit easier to see. On the y-axis, I'm going to plot ln v of the voltage. And don't forget to put the voltage inside the bracket when you're putting that on the axis, like so. Okay, on the time axis, on the x-axis, I'm going to plot time. Okay, and that will give me a straight line with a negative gradient. How do I know? Well, because if you look at the thing that's multiplying the x-axis, which is the gradient, I get minus 1 over rc. And then on the y-intercept, I'm going to have a positive intercept, which is ln v naught. Okay, so the gradient is equal to minus 1 over rc. So that means rc, which is something that you want to find and determine, is going to be minus 1 over the gradient that you get. And the y-intercept is ln v naught. And v naught you can determine by just doing e to the power of the y-intercept. Okay, so determine all these values. And then you can compare your results and you can analyze them. So use the capacitance that you used and the resistance that you used and make sure they're in farads and ohms. Multiply them together to get RC, which is the time constant. And then you would have also gotten the time constant by doing minus 1 over the gradient of the log graph and see what you get. So do they match or do they not? And you can comment on that.